Hello, welcome. This is the next Edexcel S2 video tutorial thing. Okay, so in the last one that was probably seemed very long in terms of the duration. I mean, what else? Anyway, okay, so we looked at binomial distribution. I showed you that cumulative binomial distribution function, I think that's what it's called. Basically, you know, that table thing in the formula sheet, formula book, okay? And I said it was noted like this, which says x is binomial, x little squiggle, x is just a random variable, okay? Is distributed binomially with a b, okay? And in my revision guide I do note, and this is actually true, that's why I note it, whatever letter or letters is in front of this little bracket thing, that tells you what distribution is it. So b is binomial, and n is for normal, and we're going to look at the Poisson in a minute. Okay, and it's distributed binomially with a fixed n number of trials and p probability of success. Well, oh yeah, there's one more thing. We said as well that if this probability, the p, was above 0.5, we'd have to create this new variable, which is kind of the opposite to the x. So if x was the probability of success of something, y would be the probability that it would fail. Okay, so obviously I know these p's look the same, but really this one is one take the probability of success. Okay, but really, as I said, it's just a bit of a recap. And there's a couple of things that we've mentioned of the features of binomial distribution, and they were, you know, we've got a fixed number of trials. There's only two outcomes. It's either a success or a failure. Okay. Yeah, and the success of one trial does not depend on if the previous trial has a success or failure. So, in other words, the probabilities are independent. Okay. I think that was it. I'm sure there was another one, but that's the gist of it. Okay, so as I said, you know, weirdly enough, I'm not going to spend another 50 minutes going through binomial stuff, but it is very closely linked to this this Poisson distribution. Now, apart from it sounding like some French restaurant fish thing, well, why the hell are we interested in it? Well, there's a good reason for that. Binomial says it has to have a success or a failure, okay? Where it is, as in Poisson, is essentially, what, it's basically, sorry, so trying to get my wording right. You know, I'll have to look at this because I'll probably get my wording wrong if I try to just come up with it. Yeah, a Poisson distribution is just an event which happens at random times, okay? Poisson distribution is just a distribution of an event which happens at random in times in time or space. Okay. Now, what the hell do we mean by that? Well, a Poisson distribution is, as I said, an event that happens at random in time or space. Now, I'm not saying space is in, you know, outside the atmosphere. I'm not saying, oh, it's just, you know, it can't happen on Earth sort of thing because it's that stupid. Because it's maths and we all want to die. But apart from that, yeah. So what I mean by space is distance, okay, meters, you know, on Earth. It doesn't really matter, okay. But and obviously time is just, you know, every fortnight, every week, every hour, whatever it might be, okay. And it's written like this. Now we still say with the xing and it's distributed, but instead of writing b, obviously we write p subscript o. So p little o, and instead of writing np, okay, there's only one. These are called parameters, n and p. N is the number of trials and p is probability of success. They're parameters. That's the posh word for saying they're two things that we can take from a binomial distribution. Okay, with Poisson distribution, we just have, for the physicist in the lecture, oh, I made myself sound intelligent there. I'm really not. Anyway, it only has one parameter, lambda. Now, it's key to recognise that this lambda is representing the mean. Okay, it's not the wavelength, but then again, why the hell would it be? This is statistics, not physics. it's easy to get confused, and you're in the exam, you thought, oh, well, I'll just change this to a physics exam now, but you know, you can do that, but you just got to be prepared to fail. But you might be anyway, so that's fine. Now, you might be looking at these going, are they very similar, okay, and can we try and cram them together both in one kind of little event? Well, we sort of can, and I'm not going to go into that just yet. I'm going to leave it to the end of the video actually, but just making you think about it now. What it's called is a statistical. It's a Poisson approximation to the binomial distribution. Now, obviously, the reason I'm not going to do that is because we haven't properly explained what Poisson distribution is. Okay. Because there was a lot to talk about in the binomial stuff, there's a lot to talk about in the Poisson stuff as well. But there's one thing that I want to just highlight with you, the Poisson stuff. Now, for the binomial, we introduced that new parameter of the wavelength, that new parameter, lambda, which was the mean. Now, what the hell am I talking about? So that was for Poisson. If I said binomial, I'm sorry, my brain's in a bit of a mess at the moment. For binomial, we introduced that new parameter, new variable, y, okay? So we wrote y was binomial distributed with a fixed n number of trials and p probability of failure or success, the opposite to the first one, okay? Now, you'll be happy to, and the reason we did that is because if you remember, I'll be bringing up the table to the camera just in a minute, but I can't bother doing it because I'll be doing it later, so what's the rush? If you remember, in the cumulative binomial distribution function, which was that table to do with binomial distribution in the formula book, I'm quite pleased I actually remember the name. Anyway, in that, the probabilities only went up to 0.5, okay? Whereas if you look at, and we're going to in a minute, at the probabilities in the Poisson cumulative distribution table, or function, whatever it's called, that continues to go up. Now, initially it only goes up to 5, okay, so you can only have a mean of 5, but then if you go down, okay, you look, there's values of the mean greater than 5, okay, and obviously you can work back to that table, and the way you work through the table is very similar to the binomial distribution function, but as I said, I'll be showing you the table so we can go through that in a little bit. Okay. Okay, so just thinking what I'd go through with you next. Yeah, I think it's been mentioned anyway, pretty much. But there's a couple of key features. Now, I've talked about binomial distribution key features of limited number of events, yes or no, independent probabilities, and the probability of each outcome remains the same. So probability of success on the first trial is the same as the probability of success on the 25th trial. With the Poisson distribution, now I said it was an event that occurs at random in space or time. Okay, but if you want to put some features attached to it, if it asks you to list some features of a binomial distribution, obviously listing the features helps you when you get a question that might ask you, is it suitable, what approximation are you going to use? Now obviously you can use binomial, Poisson, or the one we're going to look at later, which is a Poisson approximation to the binomial. That sounds like some kind of white wrap thing, but it's not. Okay, anyway, so the features are, it's singularly in space and time, so basically it's just one event that we're looking at. That event is independent of anything else, okay, and it's occurring at a constant rate, so once every fortnight, etc. It's not going to happen once every fortnight, and the next fortnight's going to happen 3 times, so it's consistent like that. Okay. Yeah. Okay. So, I think that's pretty much it for the bit of introduction on the Poisson distribution. But it's kind of key. Just before I go on to the table, okay, you might get a question that is simply this. It gives you a value for the mean, okay, and it will say something like this. Find the probability that x is equal to 3. Okay. Now, when we come to look at the table, we'll find out that the table. Sure. this probability that x is equal to 3. Now, as I said, you can look in the table, but I'm just going to avoid that for the second, because this formula essentially shows you how the table works out. How the table works out the probability for each value of x, 3, whatever it might be. Okay, so well, just to show you, I don't think there's really a way to build up. I was just trying to think, is there a way to build up to this? So if we let that 3 be equal to r, okay, so we say the probability that x is equal to r, where r is just a value, okay, it's equal to e to the power of negative r times lambda to the power of r over the factorial of r. Okay, so if you sub your values, obviously your lambda here is the mean, okay, which is obviously found in your distribution notation. Okay, so as I said, that's how it comes up with the formulas in the table. Alright, so you would just, you would never really use that in terms of that, just unless the question explicitly says use use that formula, okay, to work out the probability that x is equal to 4, say. You would always otherwise just simply use the information in the table. So if you don't get that, it's quite okay, but as I said, it's fairly simple, so you can use it, and there's no reason why you couldn't use it. Okay, you still get the marks for using that, or you could look at the table. Now, looking at the table, obviously, is going to take a little bit longer. Okay, so yeah, now you should know, because when we do come on to look at the table, it's in the values. It's just like the binomial cumulative distribution function table thing, where it's got values of x less than or equal to. So if you're looking at the probability that x is equal to r, the table will be in terms of x is less than or equal to r, okay, where r is a chosen value, say 3. Okay, so what you'd have to do if it asked for the probability that x equals r, but the table's in terms of probability that x is less than or equal to r, okay, say let's give r a value of 3, okay, let's stick with that. So we want to find the probability that x is less than or equal to 3, okay, without looking in the table. And we have to use this formula, okay, but this is in terms of less than or equal to, okay. But because it's less than or equal to, okay, and we want to work out the probability that x is 3, okay, well, it's the probability of x equals 3 plus the probability of x equals 2 plus the probability of x equals 1 plus the probability of x equals 0. Now, again, it's just a case of knowing that in each of these cases, r is whatever the number is. So in the first one, r will be 3, r will be 2, r will be 1, r will be 0. One of the things that you might get stuck on when you're subbing in the numbers is what's the factorial of 0? Now, just to put it out there, the factorial of 0 is 1. I'm pretty sure you remember that, but so when you sub it in, the factorial of 0 is 1. Okay, so that's what you'd do if it wanted you to work out the probability that x is less than or equal to 3 without using the table. But as I said, you would most likely just look in the table. Now that formula is really helpful when the given value we're trying to work out is not explicitly in the table, in terms of if r is 3.7, for example. Obviously, the probability in the table is not going to be 3.7. I think it goes up in 0.5. So, as I said, that would be helpful if it was a value of r, okay, where your probability of x is equal to something, where that specific value is not listed in the table. Now, it most likely will be, but if it isn't, then you can use that formula. But you have to follow this principle, okay? But if it's just working out the probability of a single value, that formula is completely okay. But really, you're not going to use that formula very much in the exam. Okay, so just nice to be aware of it and what each of it means, but really, we're not going to use it in any great context. Now, as I said, the table is very, very similar to the binomial cumulative distribution function. Okay? Well, I think probably, just thinking, there's the best way to explain through a question, or yeah, I think probably the best way to explain it through actually, you know, change my mind. I'll just simply bring up the book and we'll just show you what the table looks like, okay? I mean, obviously you can get it online, but I can guarantee quite a few people watching this video will be like, I can't be bothered. So, one sec, I'll just find the page and then I'll adjust the camera. So I'll just pause it, I'll find the page. So, hello and welcome. This is just the table, as you can obviously see. Now, I was talking about how this is very similar to the binomial distribution table, and that's because they both say the value of x is less than or equal to x. So if you add the value of that, we've got p equals p, the probability that x equals r, where r is just a number, r is one of these numbers here. In other words, p is equal to x less than or equal to little x, and these are little x's obviously. Now these lambdas just represent the mean, but you see it only goes up to 5, but then if you look down you'll see there's more values there, okay? And you do exactly the same, you just look whatever your mean is, okay? You look and then whatever your x value is, okay? So the probability that x is less than or equal to 3, so you look at where x is 3 for your desired mean, okay? Whatever your mean might be, and then you look down and across and you spot whatever it is you're trying to look for. Okay, so that's pretty much a basic analysis of this Poisson cumulative distribution function. Now, as with the example before, when we were looking at the binomial side of things, okay, we said, well, it says the probability that x is less than or equal to little x, so the probability that x is less than or equal to 3 is a probability of 3, 2, 1, and 0. So you might, you know, if it asks you probability of x is 3, you do the probability that x is less than or equal to 3, and you would take away from that the probability that x is less than or equal to 2. Okay, so it's a very, very brief summary, and it's probably something you should be kind of aware of already. But as I said, that's just using a table. Now, one of the questions they might ask you is say, you know, given that the probability of something occurring must be greater than 99%, and we'll go into examples like that in a minute, but you would look for the value which is on your mean, okay, so you'll be given a mean, let's call that 0.5 because that's the easiest, and you go, it's got to be greater than 99% or 0.9990, okay, so the first one would be 3, okay, so that's be your x value. Now, as I said, we'll come on to questions that make that a little bit, turn that into a bit more, to something that makes sense. Okay, so, 1 second. Okay, so, for a Poisson distribution, the mean, as we know, is the only given parameter, and it's represented by this lambda. Now, another key thing to recognise about the Poisson distribution, okay, trying to sound intelligent, is that the variance is also equal to lambda. So therefore, the variance is also equal to the mean. So for a Poisson distribution, the mean is the variance, or the variance is equal to the mean. Okay, now I just wrote down again the notation for a binomial distribution, and this is where a little bit of crazy maths comes in. Crazy enough because it's maths. Okay, now if you look at the two tables, the binomial distribution table and the Poisson distribution table, you notice they're very similar in terms of, well, maybe not specifically the layout, but the values they have. And you might have to be a bit anal to spot that, but you know, what I'm saying here is, if you were finding a value that, say, if you've given two similar situations, okay, so I'll become more apparent, okay, basically what we've got here is just two types of distributions, and they are very kind of similar in style. Okay, so just to recap, binomial distribution is where we had a yes or no, a successful or an unsuccessful outcome. The probabilities are independent, there's a fixed number of trials, and the probability stays the same. Whereas the Poisson distribution was a random event, an event that occurred at random in time or space. So they're both about events, okay, in the sense that you either get a good outcome or a bad outcome. And you could kind of relate that to Poisson distribution by saying, well, it's a good outcome if in terms of if it's constant, if that makes sense. In other words, would be a Poisson distribution. So maybe that's not the best explanation of how we can combine them. The short here at hand is, this is what we're doing as a Poisson approximation to the binomial distribution. Now, I'm not going to put on a gold chain and start doing some wrapping, because I'd be crap at that. I'm probably wrapping a Christmas present. That's the best wrapping I can do. Anyway, this works, okay? So basically what we're going to do is combine these two distributions as one, okay? But quite clearly you can see in the binomial distribution we've got two parameters. One of n, okay, which is the number of trials, remember, and p, the probability of success. Whereas lambda, okay, in the Poisson distribution is just the mean. Okay, so for the lambda, okay, for the mean, which is this, the variance of mean, is equal to n times p. Just make sure that's right. Yeah, okay. Now this only works if n times p is less than or equal to 10. Okay, so if n times p is less than or equal to 10, we can use this idea of something called the Poisson approximation to the binomial distribution. And to break that down, what we're doing is we're using a Poisson distribution to answer a binomial distribution question. So what essentially we're doing here is we're taking a question that could very well be answered in a binomial distribution format, but maybe we choose not to because maybe the values aren't on the table, such as, you know, our value of the n. Okay. Now there are different tables in your binomial distribution cumulative function, but n, there's not a given value for every single possible value of n. Okay, and this is where this comes in. Okay, now there are many other reasons, and you'll come on to different questions. You may get questions in the exam that say use a suitable distribution, so you can use either binomial, the Poisson, or the Poisson approximation to the binomial. Okay, so hopefully you're distinguishing between the Poisson, which is just an event, you know, distribution of an event that occurs at random in space or time, whereas a binomial is where it's a success or a failure, and it's kind of the probabilities concept fixed on the trials, etc., etc. Okay, so when n times p is less than or equal to 10, we can assume that the binomial, basically, the reason why that has to be less than or equal to 10 is because there's only a very finite range where if you were to use the probabilities in the binomial distribution, cumulative function, and the Poisson distribution, cumulative function, so basically the tables that represent the probabilities for binomial and the probabilities for Poisson, they're only the same when, now I said it's when n times p is less than 10, but essentially that is true, but it's when n is a very large number, okay, so when n is large, and when p is very small. Now I say large and small, but just in contrast to each other. We're not fixing it to a relative point, saying if n has to be larger than 600 and p has to be less than 0.1, okay? We're just simply saying that n has to be bigger than p, okay? Really, by a kind of a significant amount, but there's no law that says, you know, n has to be at least this value and p has to be less than this. They just, when you time them together, it has to be less than or equal to 10, otherwise you can't apply this method. Okay. Right, so I think for this, it's probably best to go through examples. However, there is one more thing actually I do want to mention. Now, I did say for the Poisson distribution, and we've gone through it obviously, we don't use this other value. Now, when I say this other value, what I mean is this other variable. Now, if you do recall, you managed to push yourself through all of the binomial distribution video, I did introduce another value, or variable, okay, where I called that variable y, okay, and in essence what that meant was this here is the binomial distribution of the random variable x, okay. X could be, say, the probability of a successful outcome or whatever you want to achieve, okay, and p was a probability that that would happen, okay. So what I also said, I introduced this other idea that the random variable y, which is say if you wanted x to be, you know, a success, then y would be the failure, okay. So the variable y is distributed binomially, would be the same number of fixed outcomes, okay, at n, or trials even, and p, well, that's the probability of success in x, okay, so you need to do one take that. And the whole reason behind that was because the binomial cumulative distribution function, that table for binomial, only went up to 0.5. So any value greater than that, we'd have to look at it the opposite way round. Okay, so hopefully that makes sense. Now, what we're going to do, so that was just a recap, and because this is a Poisson approximation to the binomial distribution, what we're essentially looking at here is a binomial distribution question. We're applying it to the Poisson distribution because there might be a case where we can't answer it just simply through using our methods for binomial distribution. Some of them you can do, there's no problem at all, but if n times p is less than or equal to 10, there's no reason why you can't use this route. So I think I've hammered that enough in your face. Okay, so I think the best idea now is probably to go through a few examples of a question. Now the first example I've got lined up, okay, so over here. Just choose one. Yeah, so the first example I've got lined up doesn't refer to that y variable business, okay? So basically we're just going to stick with our standard knowledge of binomial and Poisson distribution. So I can show you pretty much what a Poisson approximation to the binomial is. Now, because we're using a Poisson approximation to the binomial distribution, it should give us the same answer as if we worked the question through, as if it was a standard binomial distribution question. So, as I said, you might want to have a go at this as well. I think I'll go through it anyway, where we can check that this answer gives the same answer as if we just used the binomial distribution part. Okay, so I'm not just saying it for the sake of you'll believe me and it works, so believe me. And if I did that all through my life, I'm pretty sure I'd get slapped, but that's happened anyway. Anyway, okay, so this particular question says, in a certain factory there are 2 accidents per week. Assuming the number of accidents per week follows a, oh, one sec. No, sorry, actually, that's the standard Poisson question, sorry. Sorry, one sec, I've just found a question that's just one of these, I do apologise. Sorry, just had to choose a question that was probably a bit better. Okay, so this particular question says, the probability that a certain type of chocolate biscuit is double wrapped, so it just doesn't really matter. Okay, don't really understand. Well, obviously we do, but shut up. The probability that it's double wrapped is 0.01. Use a suitable. Okay, so it doesn't explicitly state which approximation to use. Okay, to find the probability that in a box of 60 biscuits, A, none are double wrapped, B, at least 2 are double wrapped. Okay, now let's just note down all the bits of the information that were given in that question. Okay, so the first bit is the probability that they are double wrapped. Okay, so you might want to note that down. So probability they are double wrapped. Okay, so this is, in other words, the successful outcome. Okay, we are told that it's equal to 0.01. Okay, and we're told that there's a pack of 60 biscuits. In other words, there's 60 attempts that we can find a double wrap biscuit. Okay, so n is equal to 60 because there's 60 trials. Don't be put off by the fact it doesn't explicitly say trials. It very rarely does, to be honest. It's just you have to pick out the fact that that is a trial, because well, what else would it be? Okay. Anyway, okay. So the first one, part A, says find the probability that none are wrapped. So it's P is equal to x equal to 0. So the probability that x is equal to 0. In other words, probability that there are no double wrap biscuits. But before we do that, we need to know what type of distribution is this. Well, we're told that there's a probability of a successful outcome and a number of trials. well, we've only got 2, okay, and there's only one that has 2 parameters, and also it fits the number of trials and the probability of success, which actually could help you. If you didn't spot this was a binomial distribution, this might have helped you, because there was only really 2 distributions that we know so far, so Poisson and binomial. Okay, so it's got to be one of them two, because it says using a suitable approximation. Now, obviously we can use, and we're going to use, the Poisson approximation to binomial distribution, but we'll come on to that because we need to build up to that. So we need to decide first, is it binomial or Poisson? And quite clearly, from what we're going to go on to later, it's obviously quite clearly going to be binomial. But you should spot that is from the fact that we've got A, 2 parameters, and B, one is the number of, okay, well, actually, yeah, you look at your 2 types of distribution. One of them says the mean, neither of them are the mean, okay, just says probability. You could say maybe the probability of double wrapped is a mean. Well, it's not, because it isn't. Okay, so therefore, the only other distribution must be the binomial, and we should have enough information to be going from. Okay, so obviously, depending on what the question asks, is depending on whether this is the variable or not. Okay, so in other words, do we need to include this y variable, the probability of failure? Okay, so hopefully we've determined that it's the binomial distribution. So the first thing that you always do, and I've not mentioned it already, I'm sorry, is in these questions, okay, so in your binomial distribution questions and your Poisson, and even these ones that I'm going on to now about the Poisson approximation to the binomial distribution, you always say, what is your x variable? In other words, the variable x, it's a random variable, what does it represent? Okay, so in this case, you would say, let x be the random variable. I'm just going to write RV. Okay, the random variable that the x be the random variable, the number of biscuits double wrapped, because that's what we want to find out. Number of biscuits that are double wrapped. Now, it would be a good idea if you could to load up the table at this point. However, I will be showing you, I'll just be stating the values and then proving you that are true. I'll just show you them. But I'll work through it at the moment, assuming that you've got some kind of table of it, well, some kind, there's only one kind, assuming you've got a table in front of you. Okay, so what can we do from this? Well, firstly, obviously we need to write down the notation, okay, just to help us see where we're going. Okay, so it's binomially distributed with a number of trials n, 60, and a mean of, a probability of success 0.01. Okay, so you need to now state what approximation distribution you're going to be using. Okay, so quite clearly it's binomial, but is it? Okay. Let's just do this as we were looking for the binomial. Okay, so let's attempt this as I said, we were just doing the binomial. Now, the quickest way you would say is well, just as a binomial cumulative distribution function, isn't there? So why don't we just use that one? Okay, so I've kind of just sorted out the focus so you can see it now. Okay, so just to reiterate, we want to find out the probability where x is 0. Okay, so that appears to be there. Sorry. Okay, and we want the n to be 60 and the probability of success, which is little p, to be 0.01. And you can quite clearly see straight away that that is going to be a problem. First of all, on the probability scale, well, we've only got 0.05, so we don't have that. And also, we go, okay, well, we've got n to be 60. Let's try and find n to be 60. Well, if we keep going down, okay, and you could go all the way through the table, okay, and you would not spot, okay, 60, because it only goes up, and then we could continue going, so that's 30, it goes up to 40, and then it goes up to 50, and then that's the end of the table, okay, then it starts off with the Poisson. Now, hopefully that makes sense. That's the reason we can't use the binomial distribution, the cumulative function for it. Okay, sorry. Now, I do admit that you could use the binomial equation, okay, which is okay, just derived straight from the simple equation that you get given in your formula sheet, which says the probability that x is equal to or greater than, this is the formula, okay, so the probability is that x equal to little x, it's equal to n, okay, which is obviously in this case 60, c, okay, choose x, okay, you put that in brackets, and you times that by p to the power x, probability of success to the power x, times 1 take p to the power of n take x, okay? And then you would continue that, raising the power of p by 1, okay? Sorry, no, not raising the power by p by 1, sorry, decreasing power of p, sorry, you're decreasing your value of x and increasing your value of n each time, okay? But that's if you were working out a set amount of values, but that's simply just working out that p is equal to x is equal to, probability of x being a certain value. But if you're just working out one value, you can simply sub in numbers, okay, so n would be 60, probability of success would be 0.01, and x would be 0, okay, so you could sub it into there and you would get a value, okay. Now that's the easy way to do it, but obviously we're going to look at the Poisson approximation to it. Okay, so we need to turn this into some kind of Poisson distribution. Now, to make sure that we can do this, one of the key terms that I kind of labelled here, to do this, we need to make sure that n times p is less than or equal to 10. Okay, and quite clearly, it is. 60 times 0.01 is 6. Okay, so, or 0.6, 6. You get the idea, it's going to be less than 10 anyway. I'll embarrass myself with the simple calculation errors. Okay, so hopefully you get that. So we can prove, now you might want to write that down and simply say, because n times p is less than 10, we can use the Poisson approximation to the binomial distribution. So find the question again. Sorry, I do apologise. Yeah, there it is. Okay, so, and it follows my principle that n is going to be very large, where n is 60, and p is going to be fairly small, very small in comparison to n. Okay, quite clearly it is. N is, p is 0.01, and n is 60. Okay, so we can use this function, but what the hell do we actually do? Well, if lambda, the mean, okay, is equal to n times p, we can simply sub in lambda to be n times p. We know n times p is this 60 times 0.01, which is 0.6, not what I thought. Anyway, so the next stage you would do is say n times p is equal to 0.6, which is therefore less than or equal to 10. Okay, obviously less than, but it includes equal to as well. So therefore we can use this function. And what we do is we write it out as a Poisson distribution. Okay, so x is distributed, x follows a Poisson distribution, okay, with lambda being 0.6 and lambda is the mean, so we just write 0.6 there. Okay, and now we can simply either use the Poisson equation that we've got in our books, okay, or we can look on the table, okay, and either would be completely acceptable. Actually, no, sorry, there isn't a formula for, what the hell am I going on about? There isn't a formula for Poisson. Yeah, what the hell am I going on about? Yeah, there is a Poisson distribution function. Okay, and it's the probability that x is equal to x. Okay, it's e to the power of, sorry, this isn't the best, is it? But you get the idea. Well, I say you do, I'm not you, so what do I know? Sake. Yeah, e to the power of negative lambda times lambda to the power of r over the factorial of r. Okay, so as I said, there's a couple of ways you can do this. You can either, firstly, just answer this question using that the binomial equation there, okay, or you can use because we can't look in the book for the binomial distribution, okay, so we could have a try at looking in the book for the Poisson distribution and see if it fits in the table, but we know if that doesn't work, we've still always got this other alternative of using the Poisson equation there. Okay, and if my memory serves me right, we don't have, doesn't fit in the book. Okay. Okay, so you have to remember our value of n, okay, it is still the same, our value of n is still 60, our value of p is 0.01. We're not going to necessarily use that, but we've not changed the question, so you still have to remember n is equal to 60. Okay, so let's have a look now and see if that we can find it in the table. Hello, so now this is the Poisson cumulative distribution function, and what we're going to use it for is simply to find out the value that the probability that x is 0. So in other words, the probability that x is less than or equal to 0 is simply the probability that x is equal to 0. Okay, and we need the mean lambda, okay, to be equal to 0.6. Okay, so quite clearly, well, we've got x to be 0 there, but we've got no 0.6. Okay, and even down there, we've still got no 0.6. Okay, so we can't use this table to answer that question. Okay, so what we have to do instead is use the standard equation that I've got on the board there. Okay, so as I was mentioning, we have to simply use that equation. But with these types of questions, we need to go through each method. Can I use this method? Can I use this method? But you always need to say as well what your random variable x is. Okay? So, as I said, it's a case of using that formula. Now, what we want here is the probability that x is equal to 0. Okay? So we sub x to be 0, which would be normally represented by little r. Okay, so we'd sub it into this equation now. Well, you should know that the factorial of 0 is simply 1. So, factorial of 0, lambda, the mean, well, that's 0.6. Okay, and r is 0. So it's the probability of x is 0 is equal to e to the power of negative 0.6 times 1 over 1. So it's just e to the power of 0.6. Okay. And if you shove that in your calculator, you should get a value of 0.44, I think it is. Okay, and obviously you round it to however many decimal places it asked you to in the question, or significant figures, whatever. Okay, so that's one type of question. Now the other type, as I said, is going to be bringing in this idea that we mentioned in the Poisson, stupid thing, that we mentioned in the binomial distribution. Now, as I said, we're basically here answering binomial distribution questions and turning them into a Poisson distribution. Think of it like that. We're just answering it as though it was one. That's essentially what that Poisson approximation to the binomial distribution is trying to say. It's just a fancy way of saying we're using the Poisson distribution to answer a binomial distribution question. Anyway, okay, so obviously that wasn't one. Well, it was, sorry, yeah, it was. But in the binomial distribution, we introduced that random variable y, which was just, if x was the random variable and it was distributed binomially and it was looking at the successful, what you wanted to achieve, well, y, obviously, therefore, would be looking at what the distribution of what you don't want to achieve. But you may have to use that to be able to use the binomial distribution table, because as I said, the probabilities only go up to 0.5. Okay, so I'm assuming you know what I mean by this y random variable business. If you don't, then I do have a S2 revision guide actually, which I could email to you if you just put a comment in the links below. If you just comment in the video, what the hell am I saying? Just comment and I'll email it to you. I'll sort it out. Okay, so anyway, this next question it's going to require this use of this y variable. Okay, so let's rub this off. Okay, so the question says a gardener states that 95% of the daffodil bulbs, bulbs, will produce flowers the following season. 100 bulbs are bought. Okay, use a suitable approximation. Okay, again, it's not specifying, so you can either use the Poisson approximation, the binomial distribution, or the Poisson approximation to the binomial. But first we need to see, what is the information it's actually given us, okay? Because that will give us a bit of a clue into how we can answer this question. Okay, so anyway, we're told that 95% of the daffodil bulbs are likely to produce flowers the next season, basically just turn into flowers, pollinate, etc. Okay, so we're also told that 100 of these flowers, bulbs are bought. Use a suitable approximation, so as I said, it's not specifying, to estimate the probability that at least 96 of them will flower next season. Okay, so what we've got here, we're looking at, we're asking for the probability that at least 96 of them flower. So we could have more. So what we're asking for is a probability that x is greater than or equal to 96. Okay, and we want whatever that gives us. That's going to be a probability that we need to answer this question with. Okay, we're told that that 95% of them will flower the following season. Okay, so we want 96 of them to. What's the probability that 96 or more turn into flowers? But we're told that 95% of them already will. So therefore, the probability of success, little p, is equal to 0.95. Now, alarm bells should be going off in your head that. No, not just yet, sorry. Well, maybe they should, but anyway. Okay, so we also need to. What other information we can in this? Told that 100 flowers are. Bulbs are bought. So there's potentially 100 different bulbs we can try and see if they turn into flowers. In other words, there's 100 trials. Okay, so little n is equal to 100. And you can quite clearly see, therefore we've got n and p number of trials and probability of success, which only relate to the binomial distribution. Okay, so it looks like it's going to be that type of question. Okay, but you need to now state, as before, what the random variable x represents. Okay, so obviously, first of all, you need to state that. Okay, so you say, let x be the random variable that the flower pollinates. That the bulb turns into a flower, sorry. Okay, now the next thing I would do is write out in a notation of a binomial distribution, okay? So you're showing that you're using the binomial distribution. So x is binomially distributed with a number of trials n, which is 100, and the probability of success 0.95. Now you should know straight away that the common thing that we said among binomial distribution, because when we go to look at the graph of this, okay, when we're going to answer this question, we'll look for where x is 96, okay, and obviously take one away from that. But what we're looking at here is the probability of success is higher than 0.5, so we can't look in the table because the probability of success doesn't go beyond 0.5 in the table. Now the reasons I've done that, probably quite lazy, but probably when you do a bit more maths, to be honest. I'm not going to say lazy when they've filled out several pages of tables for us, but you know, they obviously couldn't be bothered to doing this. Anyway, sorry, coughs me, I'm kind of dying at the moment, you can tell. Not jumping around as much. I don't even know why I'm just trying to apologise. My video, I'll do it at one. Okay. Right, so what we do in this situation, okay, obviously we can't turn it into, you may go, well, we'll just simply turn it into a Poisson distribution, okay, because that's essentially what we've been doing so far. But if you look, one of the key things we need to have to be able to assume it's now a Poisson approximation is have n times p, in other words, the number of trials times the probability of success, to be less than or equal to 10. And quite clearly, 100 times 0.5 is quite clearly greater than 10. So we can't do it just yet. So before we turn it into a Poisson approximation, we need to make it so that n times p is less than 10, but still keep the principle of the question there. And what I'm trying to say there is we need to come up with this y variable. So it's now just like we were trying to convert it so we can now use it as a binomial distribution question. Okay, so we'll come up with a new variable, y, and obviously we'll state again what the random variable y is, but I simply can't, can't be bothered. Okay, so you just say let y be the random variable that the bulbs do not turn into a flower. Okay, so again, y is binomially distributed with n, well, still 100 trials. Okay, but this time it's one take 0.95 because 0.95 is the probability of a successful outcome. Okay, and obviously we're looking at the variable y, which is the distribution of the unsuccessful outcomes. And obviously, in a binomial distribution, we can only have successful or unsuccessful. So it's one take probability of a successful outcome. So it's 0.05, in other words, one take 0.95. Okay, so now we've got our value for n and our value for p. Okay, now bear in mind, you may think that p is probability of success, and we've got probability of failure here. Well, we treat it in the same way, just because we kind of go back on ourselves, if that makes sense. Okay, so now, does n times p, we haven't changed the question at all, in terms of we haven't created a new situation. It's still the same situation, but we're just looking at it from the angle of failure. Okay, so is n times p less than 10? Is 100 times 0.05 less than 10? Well, yes it is, because it's 5, okay? So therefore we can say n times p is equal to 5, which is quite clearly less than or equal to 10. Okay, so therefore we can use, so therefore the next thing you would state, you put a little thing going, as n times p is less than or equal to 10, we can use the Poisson approximation to the binomial distribution, etc., etc. Again, I can't remember writing all that, so, you know, I don't really care. Right, so now we've got the situation where we've come up with this variable y, but we're going to turn it into a Poisson distribution. Now, we can't go back to using the random variable x because, well, that would just be like, well, what's the point in turning it into a random variable y here, and then using the random variable x, which is the probability of success, really. Okay, well, we can't do that, and that's purely because n times p in that situation, 100 times 0.5, is quite clearly greater than 10, so we have to use this other variable y, okay, which is the probability of failure, pretty much, okay, and that's less than or equal to 10, as it's equal to 5, so we can use that. So we have to stick with this random variable y. Okay, so when we write this Poisson distribution out, we essentially have to write the y variable. So the y, and you don't need to say what y is again if you've already done that, it follows a Poisson distribution, okay, with a mean lambda, okay, and the mean is equal to n times p, which we know is 5. Okay, so the y variable is follows a Poisson distribution with a mean of 5. Okay, so again, there's a couple of ways that we can do this. Now, we want the probability that we have to still focus on what it's actually getting us to answer. We want the probability that at least or more, so we want 96 or more of these bulbs to turn into flowers. Okay, so because we're looking at it from the context of failure, we need to consider, well, what was, if we've got if we've got 96 or more that must pollinate, must turn into flowers, that means we can have at most, so at the most, we can have 4 that don't. If we have any more, then the probability that so if there's more than 4, okay, that don't turn into flowers, then we can't have that there's at least 96, okay, that do turn into flowers, which is obviously what this question is asking. Okay, now as I said, you could just get that because the probability, the failures and successes must total to 100 because that's the total number of trials, and in the binomial distribution we can only have successes or failures. Okay, so if it doesn't fit them two, it's not a binomial distribution. Okay, so anyway, we have to say, well, in this case, the probability that the x is greater than or equal to 96, okay, is equal to the probability that y is less than or equal to 4. Okay? Now, what I'm going to do now is a little bit weird if you didn't watch the binomial distribution video. I'm just going to assume that this y variable, because there's no table for y, but it follows the same kind of principle that x does, okay, but really we're just extending the table almost, okay, so that we can include x is greater than or greater than or at least at least 96, and it can be greater than. Okay, but as we don't have a value for x is equal to or greater than 96, there's only 100 possibilities. There's only 100 trials, so therefore, if there's more than 4 that don't turn into flowers, we can't. This question won't make any sense because we won't answer it. Okay, so what I was trying to say there, I'm trying to waffle it all out, is we've turned it into a random variable y, but because it still follows the exact same distribution, we can just treat y as though we're going back to x, but we're not really. Okay, essentially what that means is we're assuming that x is a random variable that the bulb turns into a flower, so either it does or it doesn't, but even if it doesn't, it still follows a binomial distribution. Okay, but we're just, with this whole idea of a Poisson approximation to the binomial distribution is meaning we're answering a binomial distribution question in the context of a Poisson distribution. Okay, so we need to look in the table where x is less than or equal to 4. Okay, now it says y is less than or equal to 4, but remember, y is just a random variable like x is. Okay, so that's all x means, it's just a random variable and apply it to whatever situation you want. Okay. Now, hopefully you've got the idea of the, because we're looking at it from the context of a Poisson approximation, we have to look in the Poisson cumulative function table. Okay, so as I said, I'm pretty sure you get the idea of how to use one of them, so I'm not going to waste your time trying to get the camera in focus and going, holding this and shaking it about because I can't keep my hands steady. Anyway, embarrassing. Okay, so I'll just find the value. Okay, sorry, second. So you could do it from the context of a binomial and just follow this, you could look in the binomial distribution table if you wanted to, but obviously we don't have a value for n is equal to 100. Okay, so we have to use this Poisson approximation. Okay, when we don't have a number of trials that's 100, n 100 in the binomial distribution table, so we have to look in the Poisson. Okay, that's why we converted it. So what we do here is we say, right, we need to find the probability that x is less than or equal to 4. Okay, so you just look at the value x equal to 4 because the table is less than or equal to values of x. Okay, so look at x to be 4 and we want the mean, okay, which is this here, to be 5. So you look in the column where we've got 5 and x to be 4, okay, and you get the probability, therefore the answer to this question is 0.4405. Okay, so that's your answer to this question. Hopefully that makes sense. Now if it doesn't, as I say, I will be doing a S2 revision guide. I've definitely finished it by this point anyway, by the time this goes online. Okay, so if you do want the Poisson chapter of that revision guide, it's now completed, please do send me a message and I'll try and get it out to you as soon as I can. But essentially, to summarise this up, okay, Poisson distribution, you can either use it on its own, if it just simply states use a Poisson distribution to answer the question. Well, it won't say that, we'll give you a question, it'll say use the Poisson distribution to answer it. Okay, you've just got to remember that the mean is the same as the variance, okay. The Poisson distribution has only got one parameter, okay, which is the lambda, which obviously represents the mean, okay. And use the table in exactly the same way. If it just simply said, this is the Poisson distribution, it's got a mean of 5, okay, find the probability that x is less than or equal to 4, you just simply look in the table, that's very easy. And it's slightly harder looking at the binomial side of things, okay, where we take the concept of, that x is a random variable of successful outcomes, okay, and then we can apply it to that we introduce this new random variable y, okay, which is essentially the probabilities, the way probabilities are distributed that don't come to a successful outcome, okay, and obviously they both have to total to, so you have to have the number of successful outcomes plus the number of unsuccessful outcomes equal to the total number of trials, because as we mentioned, okay, you can, in binomial distribution, you can only have a successful outcome or a negative or a unsuccessful outcome. So obviously the total of them two combined must be the total number of outcomes. Okay, so I don't really think I need to do any more questions as such on this topic. Oh, sorry, it's because I have hay fever. Okay, but if you do want me to go through a few more questions, please do let me know. Comment below. But I'm just trying to get through the majority of the S2 syllabus, and I'll be doing some past papers, hopefully quite shortly. Alright, so thanks for watching, hopefully it's been helpful, and we'll see you in the next video. Don't forget to leave a comment if you want that revision guide.